the importance of ductility in earthquake resistant design. So basically, what is ductility? So ductility is the ability of a material to take large inelastic deformation before the final collapse. And it is the ratio of the ultimate strain to the yield strain. And why it is important? Ductility is important because if we are making use of the inelastic part of the material strength, then we will be able to make full use of the material strength, and it is economical. And also we can make use of the response reduction factor in our design if the material is ductile. And now coming to the ductility, the level of ductility. So basically there are five level of ductility. So for a structure to be ductile and for a structure to have a good collapse mechanism, the four level, these four level are important. That our material should be ductile, the section should be ductile, and our member should be ductile, and the connection of a member should be strong and stiff. So if these four things satisfy, then our structural behavior will be ductile. Now coming to the meaning of ductility of a material. So what do we mean by the ductility of a material? So ductility of a material is the ratio of the ultimate strain to the yield strain. And we want our material to be ductile. And and also, as you know that lower grade steel has better ductility compared to higher grade steel. So it is also seen in practice that lower grade steel have better earthquake resistance, better performance during the earthquake. So it is recommended to use lower grade steel compared to higher grade steel for better earthquake resistant design. And also we want uh, basically the material nonlinearity to come into picture, but at the same time we want to preclude the geometric nonlinearity part of the uh, structure. We don't want our beam or the member should fail by buckling or by failure like warping. So these kind of failure we don't want, and to prevent them, we basically uh, uh, we basically want to preclude the geometric nonlinearity part, and that we can do by the proper dimensioning of the section. And now coming to the ductility of section. So basically, what do we mean by the ductility of section? So according to our Indian standard IS 800, there are four types of steel section. One is the uh, plastic, compact, semi-compact, and slender section. So it depends upon the D by T and B by T ratio. So if our section is slender, then the then basically the stress will not be able to reach the yield stress value, and the section will buckle before reaching the MY value or the MP value. So that type of failure we don't want. So uh, it is not recommended to use the uh, slender member for artificial design. And now coming to the semi-compact section. So semi-compact section, basically the as you can see in this graph, uh, the final stress will be uh, will reach the basically the yield stress value, and the moment maximum moment which will be developed in the section will be My. So these are semi-compact section, and compact section of the section in which basically the MP value will be reached, but it doesn't have the adequate rotational capacity. And the plastic section of the section, basically in which the stress exceed the yield stress value, and the MP will be attained, MP value will be reached, and basically the plastic section have good rotational capacity. So it is recommended to use the plastic section in a resistant design. So now coming to the ductility of a member. So ductility of a member means that basically, as I told earlier, that we don't want geometric nonlinearity to come into picture. So we want to prevent the geometric nonlinearity failure. So basically, we don't want our member to fail by buckling or by warping or these kind of failures. So uh, that is done using the proper dimensioning of the section. And also, what do we mean by ductility of member? So ductility of a member means that the member should be able to form the plastic hinges in it. And if the member is able to form the plastic hinges in it, then it is called as ductility of the member. Now coming to the joint and connection. So basically, our joint and connection should be strong and safe, and it joint should not fail before the failure of the member. Because if joint fails, then we will not be able to make full use of the capacity of the uh, member. So our joint should not fail before the failure of the member. And also the plastic hinges should not form in the joint. If plastic hinges form into the joint, then the joint will fail, and basically it is not economical. So we want plastic hinges to form away from the joint, and this we can do by giving the adequate steel near the joint, so that plastic hinges do not form near the joint. So now coming to the ductile behavior of structure. So basically the behavior of structure will be ductile if the four level of ductility are satisfied. So now coming to the ductile behavior of structure. So basically, if we do the pushover analysis for structure, then we will be able to see the get an idea of the ductile behavior of the structure. So basically, what do we mean by the ductility of a structure? So ductility of a structure is the ratio of the, if we do the pushover analysis, the basically it is the ratio of the maximum displacement to the yield displacement. So that is the ductility of the structure. And so this is the analysis I have done long time back in SAP 2000 software. So you can see that in this collapse mechanism, the hinges are forming in the beam up to the fourth story, and then the hinges are finally forming in the ground floor columns. And in this way, the collapse mechanism is forming, and the structure is finally collapsing. So this is one kind of failure mechanism, and this is the second kind of failure mechanism in which basically the hinges are forming up to the hinges in beam are forming up to the uh, third story, and then the hinges are forming in the column. So this kind of so second kind of failure mechanism we don't want. We want the failure mechanism should be of first type, so that the hinges are distributed along the height of the building. So in first collapse mechanism, this up to the fourth story, the members are entering into the plastic range, and the end story, topmost story is in the elastic range. And in this, top two floors are in the elastic range, and remaining three floors are in the plastic range. So in this second failure mechanism, we are not able to make full use of the members capacity. So this kind of failure mechanism is not recommended, because this kind of second kind of failure mechanism will be having lower lateral load taking capacity. So we want the failure should be of the first type, and so this kind of failure mechanism depend upon us. So we can design structure such that the first kind of failure mechanism is taking place, and we can also design the structure in a way that second type of failure mechanism is taking place. So this depend upon us. Now also it is seen that the material is the steel ductility is almost 300, and the section ductility is up to 30, and the member ductility is 10, and finally the structure ductility is 3. So steel is having the maximum ductility, and as we go to the final level, that is at the level of the structure, the ductility is decreasing. So This is the ductility of a ductile behavior of the structure. And so I think this will be helpful for you to understand the collapse mechanism of the structure and the importance of ductility in achieve resistance design. So, thank you.